Hello, everyone, and welcome to Glasgow Science Centre's Curious About live sessions. My name is Alicia, and I am a science communicator here at the Science Centre, and I will be joined today by Jane Breach, who is the Community and Education Lead for Drax Power Station. Jane will be telling us all about how Drax Power Station generates electricity with carbon-negative emissions. Now, before we get started, I want to remind everyone that this is a live session, so this is your chance to ask Jane all of your really important questions. So at any time during the stream, please pop your questions down in the YouTube chat section, and we're going to try and get to as many of them as possible. We have also been experiencing just a few technical difficulties this morning, but we'll try and work through them if they pop up during the session. So without further ado, I am going to hand things over to Jane for our session to get started.
Thank you for that introduction, Alicia. My name is Jane, and I am here to talk to you about Drax Power Station, which is where I work. If you could move on to the next slide, please. Thank you. So Drax Power Station is situated near a town called Selby in the county of North Yorkshire. And I'm here today to talk to you about our journey to reduce our carbon footprint whilst we supply electricity to the United Kingdom. If you're unsure where Selby is, it's the red circle and the arrow which point to the area. As you can see, we are almost in the middle of the country when you look lengthwise from the tip of Scotland to the bottom of the southern coast of England. Next slide, please. Our journey began in 1967 when the building work on the power station started. The station was planned and built in two parts. The first half started generating in the early 1970s and the second half in the early 1980s. This meant we could increase electricity output to mirror the increase in electricity use in the UK as the country became more dependent on electricity for everyday use. When the power station was completed in 1986, it used a fossil fuel in 6 boilers to generate electricity for 6 million homes and businesses. Next slide, please. Historically, coal, which is a fossil fuel, has been widely used for electricity generation. Unfortunately, fossil fuels are known to contribute to climate change. Coal is formed from plants and trees that were growing millions of years ago when the dinosaurs were roaming the planet. These plants and trees absorbed carbon dioxide during their growth cycle. When the plants and trees growing in swampy areas died, they were slowly covered in layers of sand and mud. The weight of these layers and heat from the earth eventually turned these plants into coal, trapping that carbon dioxide they had absorbed into the Earth's crust. Carbon dioxide is naturally released through the carbon cycle. We need it in the atmosphere to keep the Earth warm enough for us to live on. But when fossil fuels are combusted to release energy to form heat, they also release the stored carbon dioxide back into the atmosphere, increasing the background levels of carbon dioxide. This contributes to climate change, as carbon dioxide and other greenhouse gases trap heat from the sun, warming up global surface air temperatures. As you can see from the emissions indicator on the right-hand side, this has a large carbon footprint. About 20 years ago, Drax Power Station started to research and investigate how new fuels that they could use in their existing power station, which would help them reduce the carbon intensity of the electricity it produced. Eventually, biomass was chosen. Next slide. So, what is biomass? Click, please. Yeah. Biomass refers to a plant-based material that can be used to produce electricity and heat. Click again, please. This biomass comes from sustainable sources like healthy growing managed forests. And a managed forest uses good forestry practices to ensure continued growth. So when a portion of the forest is felled for its wood, it will be replanted with new trees. And whilst those trees are growing, foresters will periodically remove weak and diseased trees. This helps the health of the forest, allowing the larger trees to grow and sunlight to reach the forest floor, which helps plants and animals who live on the forest floor to flourish. Additionally, a well-managed forest is less susceptible to forest fires. Click again, please. All trees absorb CO2, and young growing trees actually absorb more CO2 than their equivalent older trees. This is because young trees need more energy to grow. And all the time, a forest is absorbing carbon dioxide from the atmosphere. Click again, please. So when this wood is felled, it's felled for a number of industries. Primarily, those are for construction and furniture. And then there are other industries which use the low-grade wood, like ourselves. Click again, please. So wood that is low-grade or waste from sawmills can be used for biomass. When a trunk of a tree is cut up for building and furniture, for the building and furniture industry, the sawmill produces large quantities of sawdust, which we can use for biomass. Okay, if you could click again, please. And click again. So here we can see pictures of the stages of biomass production. So the left-hand picture shows some of the wood that we use. So that's taken to pellet production mills. The wood is dried and it's chipped and then powdered. And then that powder is used to form pellets. So the powder is compressed into the pellets. So they look relatively small, but they contain a large proportion of compacted wood. Next slide, please. To understand how biomass has set the power station on a journey to reduce its carbon footprint, we need to look at the carbon cycle of the fuel and electricity generation. So if you can, imagine a world where there are no other carbon emitters. For example, no transportation, fossil fuel-based heating. Drax generates electricity with sustainably sourced biomass from managed forests. And as long as the carbon dioxide absorption rate, so that's how much carbon dioxide the trees are drawing in, is greater or equal to the carbon dioxide produced when we generate electricity, it's a balanced cycle. It's carbon neutral. Saying that, if you look at the carbon emissions indicator on the right-hand side, you can still see that there is a carbon footprint. And this comes from the production of the pellets and the transportation of the fuel from where we source it to the UK. Next slide, please. As you can see from this picture, the UK has a relatively small managed forest industry. It's not all in the middle of the country. For the purposes of this representation, it has been condensed into one area. In reality, forests are spread across the United Kingdom in small pockets. The land covered by managed forests in America and Canada is considerably more. This is understandable when you think about the land mass of America and Canada compared to the United Kingdom, and the fact that the major construction material of much of their housing is wood. The wood will need to be turned into biomass for pellets for transportation, and then they're moved by ship and rail to the power station. And this gives that wood the smaller carbon footprint, so we call biomass a low carbon fuel. Okay, if you could move on, please. Click, please. Thank you. So these are some pictures of the types of ships that we use to transport the biomass. They go up to around 62,000 tons per delivery. If you imagine a small car is around about a ton, that's 62,000 cars worth of fuel. As I said earlier, once the fuel comes into the ports, it's then loaded on the trains and transported to the power station. And we use ports in Tyneside, so Port of Tyne, in Immingham, which is northeast Lincolnshire, and also in Liverpool. Click on, please. And again. Next slide. Okay, so I'm just going to cover now how we generate electricity. So the first step to generating electricity is actually to process the fuel. So the pellets I said were small, but they're still too big to go into our boilers. So we need to reduce the size of the fuel particles. And the way that we do this is by using pulverizing mills. And pulverize is another word for crush or grind. So each of our boilers, and remember we have 6, have 10 mills to crush or grind the fuel. If you look in the top right-hand corner, you can see a picture of a ring with a circular ball in. So that is what's inside the mill. So each ball has one of these cupped rings, and the ring holds 10 steel mill balls, which roll around in the ring, pulverizing the pellets. So it's a bit like a giant pepper grinder, reducing the pellets to a fine powder like flour. So if you could click on, please. You can just see the arrows, pellets, they go through the mill like a grinder, click again, and you get the flour. Okay, next slide, please. So once we have the powdered fuel, we will send it to the boiler. Boilers do really important jobs, not just at the power station. You may have a boiler like this, the right-hand side picture in your house, which hot water comes out of, which is fed through to your taps and also to your central heating system. The boilers at Drax work in the same principle as another item that you'll find in your home, which is a kettle. So in a kettle, you use energy to heat up the water to 100 degrees centigrade, at which point the water will evaporate into a gas, which we call steam. Next slide, please. So as you can see here, we've got a plan of our boiler. So in the middle, you can see all the combusting fuel burning. So the biomass is blown into the boilers where it is burnt to release the energy it contains in the form of heat. The walls and the top of the boiler are made of metal pipes which contain water. The fire in the middle of the boiler heats the waters in the pipe to produce steam. But it's not normal steam like your kettle. Our steam is called superheated steam, which means that when it leaves the boiler, it's at a temperature of 568 degrees centigrade, which is much hotter and powerful than the steam that you would find in your kettle at home. Next slide, please. Okay, so let's bring some of this boiler to life. So the first picture on the left-hand side is the boiler house. You can see my colleague there standing at ground level, and the red square is the area that the boiler covers. So as you can see, they are really big pieces of kit. Each one is 65 meters tall and weighs 4,000 tons. And that's without the water in it. The water adds another 500 tons to the weight. The pipework in the boiler, if you were to lay it nose to nose, would cover 483 kilometers in length. And the temperature in the middle of the boiler can get up to 1,400 degrees centigrade. Next slide, please. Okay, so we've got all this super powerful, superheated steam, and we need to use that energy. So it's sent to the turbines, which convert the heat and the pressure in the steam into kinetic energy in the form of rotation. Because the steam is so powerful, those blades spin really fast. We need rotational speed of 30 times per second or 3,000 revolutions a minute. Next slide, please. So this is a picture of some of our low pressure turbines when they're not in use. And at the power station, each boiler has a line of 5 turbines bolted together so they spin at the same speed. The turbines are different sizes, which allow us to effectively use all the energy in the steam. You can see some engineers at the end of one of the turbines, again, which shows how big they are. Each one weighs 56 tons each. So it gives you an idea why we need so much power in that steam. Next slide, please. Can you click, please? There we go. So the next part of the process is the generator. And the generator actually consists of 2 parts. So we have the rotor here, which is an electromagnet, and this is 15 meters in length and weighs 82 tons. Next slide, please. Oh, sorry, that's it. Next click. Click again, please. And again, and again. And again, sorry about this. There we go. The second part of the generator is a cylinder which goes all the way around the electromagnet. We call it the stator, and it's made up of copper. If you don't know what copper is, if you could click again, please. And again, so copper is a pink metal. It is part of 1 and 2 pence pieces, and you can also see it in your house. It historically has been used for piping water in our homes. Next slide, please. Okay, click again. Thank you. So the turbines are connected to the generator. They're actually connected to the electromagnet. And so therefore the electromagnet will rotate at the same speed as the turbines. You can see the yellow lines, which are representative of the stator and the the copper parts or copper connectors in the generator. On the top right-hand side, you can see a representation of the poles of the magnet as they spin. So the magnet is cut in half lengthways. So you have a north pole running the length of the magnet and a south pole running the length of the magnet. And as the magnet rotates, the magnetic fields around each pole will induce electricity every time it passes one of the copper connectors in the stator. Next slide, please. Okay, so we're going to have a quick recap of the generation process. So first of all, we start with the fuel, which is biomass. Click again, please. So that fuel has been processed. So we send it through pulverizing mills, which reduce the fuel particle size to that quite similar to flour. Next click, please. And again. Once we've got those tiny particles of fuel, it's then sent to the boiler where we will burn the fuel. The reason that we have such tiny particles is we need really quick release heat energy in the fuel. It needs to be burnt really quickly. And we expect our fuel to go from fuel to ash, so that complete energy release in under 2 seconds. So that does need to be so small. So in the boiler, we're producing superheated steam at 568 degrees centigrade, and that steam is then fed to the turbines. If you could click on, please. And again. And then from the turbines, that rotational speed is used in the generator. So if you could click again, please. And again. and again. And then from the generator, you get electricity. So our generators produce 23,500 volts. And this is stepped up before it goes out to the national grid. So that just means that we increase the voltage in the electricity up to 400,000. And then from there, it can go anywhere in the UK. Okay, next slide, please. So you've seen how we've started to transition the power station away from a high intensity fuel, a high intensity carbon fuel, to a low one. Now we need to look at more. Now we need to look at how we reduce our impact on the environment even more. And this means looking at generating electricity with a zero carbon footprint or even with a negative carbon footprint. This is sometimes known as negative emissions. First of all, I thought we'd have a little dive into what negative emissions are. So if you could click, please. So negative emissions are processes that remove greenhouse gases like carbon dioxide from the atmosphere. Click, please. There are two ways of creating negative emissions. So one is through developing innovative new technology, which will extract the carbon dioxide from the atmosphere, or it's through using nature and nature-based solutions. Click again. So nature-based solutions include planting new or regenerating forests that we already have. It can also be looking at other things like peat bogs and other sort of areas that will absorb carbon dioxide as they grow. Click, please. The other way, of course, is technology-based. Some of the things you may have heard about are direct air capture storage, otherwise known as DACS. That uses machinery to draw in air and a process then to capture the carbon dioxide as it's drawn through the machine. Next slide, please. And when this is linked to permanent storage, it means that it is taking out the carbon dioxide from the atmosphere for perpetuity. Next slide, please. Another innovative technology is called bioenergy with carbon capture and storage, and this is what we are looking to develop. Our acronym is BECCS, and I'll continue to say that because it is quite a mouthful. Next slide, please. So BECCS can create negative emissions while also generating renewable electricity. Next slide. And this, as we really looks at that growing forest, that sustainably managed forest with that strong reparting program. Next slide, please. So, as we've covered, we use that low-grade wood and waste residues from the sawmills. They're compressed into pellets. Next slide, please. And we use that to generate renewable electricity. Next slide, please. And then we have carbon capture fitted to the power station, which allows us to capture that carbon, and like DACS, as long as it's fitted to some secure long-term storage, it can be permanently removed from the atmosphere. Next slide, please. There you go. And next slide, please. So this slide is an overview of the carbon cycle. So it covers naturally produced carbon dioxide. So that's through respiration from the forests and photosynthesis. You've got plants and animals which emit carbon dioxide. You've got decomposition from the soil. And you've also got exchange with the ocean and the atmosphere. And then in the middle, you've got us generating electricity. So this is part of that low carbon cycle that I was talking about. You've got the forests which are managed. We use the pellets to make electricity, and there is some release of carbon dioxide. So next slide, please. And click, please. There we go. So this is the same slide, but it's just showing a difference when you've installed BECCS at the power station. So this removes that release of carbon dioxide back into the atmosphere after we've generated electricity and diverts it to long-term storage in natural caverns underground. So the way that you could think of it is a bit like a reversal way of generating electricity, which took carbon from the Earth's crust in the form of coal and released it into the atmosphere. With biomass and BECCS, we can generate electricity, but by capturing it, we are returning the carbon in the form of carbon dioxide back to the Earth's crust for long-term storage. And we've calculated that we can capture more carbon dioxide than the carbon footprint of the fuel and the generation process. This means that we can help towards removing excess carbon dioxide from the atmosphere. Next slide, please. So installing BECCS is a chemical process, and it's based on a liquid called a solvent, which likes to bond to carbon dioxide. So it'll latch onto those carbon dioxide molecules. So what happens is that this solvent is sprayed on the smoke after it leaves the boiler, and we call this smoke flue gases. And the flue gas is transported to a special column, and that column allows the flue gases to be pushed up through the column while we spray the solvent down. And in the middle, that solvent is latching onto the carbon dioxide, bonding with it. That solvent, which is laden with carbon dioxide, is then sent to a regenerator. And this is where we can add heat to split apart that bond between the solvent and the carbon dioxide. This means that we can recycle the solvent back through the process, and the carbon dioxide then has been captured and can be transported to long-term storage. So this process has been happening for quite a few years now in other carbon-intensive industries to help reduce their footprint. But using it with biomass, which has already absorbed the carbon dioxide, gives Drax a unique opportunity to produce negative emissions. Next slide, please. So any questions?
Wonderful. Thank you so much, Jane. I actually found it very interesting to see how big all of the machinery and boilers were. So that was quite a new thing for me to learn. So we are going to open it up to our questions just now. If you haven't popped any questions into the YouTube chat, now is the time to do it. This is your chance to ask Jane all of your burning questions. So we are going to get started with that. And our first question should pop up. So from Heath Hall Primary School, P7, how easy is it to build a factory which can create renewable energy?
Not that easy. At Drax, particularly, we are an established power station, so we have to find the land to make the build. So that means that we have to demolish parts of the power station first. Luckily, we have bits which are redundant nowadays since we've converted to biomass. And also it's innovative for us as a power station linked with biomass. So any engineering, large-scale design project will have design challenges all the way along. So it's going to be a lot of work, but it's really exciting, and the engineers love a challenge as well.
Yeah, who doesn't like a good challenge? I agree with that. Absolutely. So let's move on to our next question, and should be popping up here. Another one from Heath Hall Primary School, P7. How do you transport the renewable energy which you make to different companies?
That's a really good question. So there is a company called the National Grid, which actually look after the transportation network. So all the pylons and the cables that you see suspended across the countryside are being managed by them. And they have the unique job of matching demand, which is users like myself and you, to supply, which is coming from the power stations and other renewable generators. So generation makes it and puts it out there, but the grid makes sure it gets to your homes.
Yeah, it's really wonderful to think when you flip on a light switch at your home, you don't always think about where that energy comes from, but like listening to this has really kind of opened my eyes to when I turn on my light switch on, the energy might be coming from Drax. I think that's really interesting. All right, we have another question, I think, about to pop up. Okay, so are there trees that make better biomass fuel than others?
That's a good question. Plant life, tree life is extremely varied and has different energy content in it, a bit like the food that we eat. There's a great raft of food and there are different calories or energy kilojoules in them. So what we do is we use trees mostly, which we find have the best energy content for us. But what we can also use is agricultural residues. So these are waste products that are left over from processes or harvesting of other crops, and they will have a lesser energy content, but we do use them as well. But predominantly, trees are better for energy.
That's really nice to know that all different kinds of things can be used, not just the trees, and that you'll use them even if they're not as good of an energy creator, which is nice and sustainable way of using the resources. So we've got a few more questions, I think, before our time is up. So let's see what we've got coming in. Why do you make the pellets if they are going to be ground up?
That's a really good question. And yeah, it sometimes it doesn't make sense, does it? Why do we do one thing to completely reverse it? So it's all about transporting as much fuel as we can with the most energy while keeping it safe. So as you noticed when we looked at the slide with the biomass, when you get wood and wood residues, it's really bulky. I don't know if you've ever seen sawdust when it's in its form. There's a lot of air in there. It's bulky. So by grinding it up into a powder and pressing it into a pellet, we are getting as much wood as we can into a small pellet. And that means we can transport lots of it, but we still get a lot of wood for our pellet. And then the other thing is that why not just transport the dust? Well, dust particles can be quite dangerous when they get to a certain concentration in the air. Wood dust does this, and also flour does this. So compressing them into the pellet gives us the safest transportation option.
Yeah, when you mentioned that the dust goes from dust to ash in, I think it was 2 seconds, that would cause a really fast reaction and probably wouldn't want that on a container ship across the ocean. So I think we've got time for one last question coming up, and let's see if we've got one. Okay, here we go. From Sam, Glenifer High School, S1. What will your next goal be if you achieve the current one set? That's a good question.
That's a good question. Do you mean just at the power? Yeah. So I'm taking that as you meaning that if we just convert the power station to BECCS. So the goal is to, at Drax Power Station, to look at BECCS and storage of carbon dioxide within the larger area of the region. So there are lots of other carbon intensive companies and an industry in the Humber region. So it's looking at collaborating with them to reduce our carbon dioxide. And it's also looking at how we can help other industries or companies also transition to carbon capture. Because, as you know, we're one country, we can't do it alone. So this technology and other technologies will need to be rolled out around the world.
I love that. We all need to work together. It's not just one of us doing it, it's all of us doing it. That's fantastic. Well, unfortunately, that is our time. Oh, do we have time for one more question? Oh, never mind. That was a question before. Sorry about that, guys. So that is unfortunately all the time that we have for today for our session. But from myself and from Glasgow Science Centre, I would like to say a big thank you to Jane Breach for joining us today and sharing all of her wonderful information. And I would love to say thank you to all of you who watched and for your amazing questions. I've had a really good time finding out more about carbon negative emissions. If you're finding that you are still curious about our future fuels, you can check out our website at curiousabout.glasgowsciencecentre.org, where we have lots of activities, quizzes, fun facts that you can get stuck into. And we will be popping up a survey link in the chat just in a few seconds. If you can click on that and give us a little bit of feedback, we would really love to know how you found our live session today. But from all of us here at Glasgow Science Centre, thanks again for joining, and we'll see you next time. Goodbye.